So hello everyone, my name is Ria Mehta, and today I'll be going over the solution for homework 2 for data structures. So to start off with problem 1, the key here is to understand big O notation. I think that's the simplest way to approach the problem. But regardless, I will list out all the different types of notations as well as their limit definitions and an intuitive way to understand them. So to start off, first we have big O, which I will be using in this problem. Actually, I'll also be using the other ones. So the definition for this, the limit definition, is we have a function, f of n, and f of n is equal to big O of g of n if the limit as n goes to infinity of f of n over g of n is not equal to infinity. So essentially we can say that f grows no faster than g. And then also, this is all on the last slide of your notes, we can also say, I put this in quotes because it's not actually a definition, f is less than or equal to g. But yeah, this is really key understanding this. For big omega, the definition is that the limit as n goes to infinity of f of n over g of n is not equal to 0. So if this limit is true, then f of n is big omega of g of n. And again, this implies that f is greater than or equal to g, again in quotes. Then for big theta, we have that the limit as n goes to infinity of f of n, g of n, it exists and it's greater than 0. So this implies that f is equal to g. So f grows at the same rate as g. Then for little o, we have that as the limit from n to infinity of f of n over g of n. If that limit is 0, then we can say that f of n is little o of g of n. And this implies that, in quotes, that f is strictly less than g. And then finally, for little omega, we have that the limit as n goes to infinity, f of n over g of n. If that is equal to infinity, then we can say that f is strictly greater than g. F grows faster than g. Note the subtle differences between big O and little o and big omega and little omega. So the best way to approach this problem is to first make some basic simplifications. So using log rules, we know that this is just equal to n. And then we also know that this is equal to n times n to the 1/2. This is n over 2 over 2. And then this is equal to n 3/2. And then I think the best way to approach this problem and properly justify your answer would be to take a couple of limits. So here we have the limit as n goes to infinity. And let's say that I want to compare this function and this function. So I'm just going to put n here because that's what this simplifies to. And log base 2 of n factorial. So we know what this bottom expansion is. So we log n plus log of n minus 1, and then we just keep on going. And this term, we eventually get to log of 1. And we know that this is going to be 0. So what this is implying is that n is less than log base 2 of n factorial, right? Because this term on the bottom is growing. And then let's do another comparison. We can say that the limit as n goes to infinity of n root n over n factorial. So here we have, this is n to the 1/2. And then we have n minus 1, n minus 2, all the way down to 1. So we can also see here that the factor of n on the bottom is going to be larger than the factor of n up here. I'll call this is n to the 3/2. So this is also equal to 0. And using this definition, we can say, oh sorry, you can't see using this definition, we can say that n root n is less than n factorial. So these are some statements that we've made. And then we can take another comparison also, just to be concrete. The limit as n goes to infinity of log base 2 of n factorial over n root n. So again, we're going to expand the top here. Log n plus log n minus 1 all the way down to log 1, and again over n times n to the 1/2. So each of these terms is smaller than this one right here. So this is also equal to 0. So we can go ahead and say that log base 2 of n factorial is less than n root n. So we have a couple of things here, but we can do only one final comparison to make our answer final. Why don't we compare this one right here and this? So I can say that the limit as n goes to infinity of n factorial over n to the power of n, this would be n times n minus 1 times n minus 2 all the way over to 1. And then the expansion of this would be n times n times n times n. So we can look over here and we can see that each of the terms on the top is less than or equal to n. So here we can make a statement that we know, since each of these terms is less than or equal to n, this is not approaching infinity. So we can say that n factorial is less than or equal to n to the n. And then if we go ahead and put these statements together, we get that n is less than log base 2 of n factorial, and log base 2 of n factorial is less than n root n. And we know that n root n over here is less than n factorial, and then n factorial over here is less than n root n. So that is your final answer for this. Moving on to the next problem, you can also apply your limit definitions here, but notice that we use big O, so I'll write the definition again to just remind us. So for f of n to be big O of g of n, we have to satisfy that the limit from n to as n goes to infinity of f of n over g of n does not equal infinity. So if we look at 2.1 here, we can see the limit. If we take this side to be f and this side to be g of n, as n goes to infinity of log 2 to the 2 of n over log base 2 to the 2 of n over 2. We can make some simplifications here. So this is just n over 2. And again, these are just log rules. And if we simplify that, we get something that looks like this, and we get 2. Notice that 2 is not equal to infinity, therefore this is true. 2.2, we do the same thing. N goes to infinity, then we're going to take 2 of n over 2 raised to the n over 2 power. And we could also make a simplification here. So I'm writing an equivalent expression. So this is like an exponent rule, so I can do this minus this, and then I can get this. And this is pretty clear. As n goes to infinity, this is also going to go to infinity, so this is false. Then 2.3, we have the limit as n goes to infinity, 2 raised to the n plus 1 power over 2 to the n. So this is really just 2 to the n times 2. Again, I'm just using some basic exponent rules, then 2 to the n on the bottom here. So I'm going to cross this out. We get 2, which is not equal to infinity, so this is true. Notice how for this problem, I've just applied the definition of big O, specifically the limit definition to assist. And I did that for problem 1 as well. Moving on to problem 3. What do we have? Okay, so we're going to consider this function that is defined recursively. And then we're going to find an expression, g of n, such that f of n is equal to big O of g of n. And if we put that into words like I had put into on the previous slide, we can say that we are trying to find a g of n such that f of n grows no faster than g of n. And if I were to say that informally, this is how I would say it. And it's pretty important to consider. And also note that it does ask you to be as simple as possible. So I think the best way to start out would be to see how this function turns out. So we'll just take some values of n and compute it. So when n equals 1, f of n is equal to 1, right? Because if n is equal to 1, then it's just 1. When n is equal to 2, f of 2 is going to be equal to 2 times this summation here. And the summation goes from I to n minus 1. So that's just going to be f of 1. And we know that f of 1 is 1, so this is 2 times 1, which is 2. When n is equal to 3, we get f of 3 is equal to 2 from I equals to 1 all the way to 2. So f of 1 plus f of 2. So this is just equal to 2 times 1 plus 2, which is 2 times 3, which is 6. And we'll do one more. F of 4, 2 times f of 1 plus f of 2 plus f of 3. That would be 2 times 1. 2 times 1 plus 2 plus 6. Squeeze it in here. 2 times 3 plus 6 is 18. So we can see that we have certain values here. Let me just make this smaller. Okay, just give myself more room. So here we have n. I'm just going to organize this so that we can do this next part. So I'm just listing out the values of n here, and then the values that we computed. So now we have various values for this function for certain values of n. So now we want to find a g of n such that f of n grows no faster than g of n. So g of n is a function, it's an expression. And what I'd refer to here in your notes, you have a hierarchy of functions. Something along those lines. I don't know what it's exactly called, but it's definitely something like this. It's basically like growth. So like, certain things grow faster than another. So like n doesn't grow as fast as n squared, which doesn't grow as fast as n cubed, that type of thing. So I refer to that. So the key here is that you want g of n to act as a bound on f of n. So f of n all the values of f of n should be less than or equal to whatever we find g of n to be. So I mean, I don't know what g of n is. We can try out a couple different things. We can try out some sample g of n's here. So let's say my hypothesis is that g of n is n. So we're saying that by making this statement, I'm just trying to say that f of n is equal to big O of n. So that means that f of n grows no faster than n. So if that was the case, this would be like this. We can see that's not true. 6 is bigger than 3, and 18 is bigger than 4. So the order of f of n is definitely higher than n. So the natural guess would be to go to n squared. So we have 1, 4, 9, and 16. I just squared these values of n here. So we can see starts to look good. 1 less than or equal to 1, 2 less than or equal to 4, 6 less than or equal to 9. 18 is not less than or equal to 16. So we know that's not right. Another guess would be 2 to the n. So 2 raised to the power of 1 is 2. 2 raised to the power of 2 is 4. 2 raised to the power of 3 is 8. And 2 raised to the power of 4 is 16, I believe. And again, same case, 18 is not less than or equal to 16. So I mean, I could try out another function too. We can maybe try out 3 of n. Here we can say that 3 to the first power is 3. 3 to the second power is 9. 3 to the third power is 27, and then this is 81. You can clearly see that 1 is less than or equal to 3, 2 less than or equal to 9, and so on. So we can say that f of n is equal to big O of 3 to the n. Yeah, that is the solution.